In a conventional amplitude modulation, the envelope of the modulated signal is proportional to the modulating signal, as we can see in this example here. In this case, it is possible to use a very simple detector, an envelope detector, to recover the modulating signal. The only thing that is necessary is to remove the mean and to rescale the output of this envelope detector. And the implementation of an envelope detector is really simple. A diode to rectify the signal, and then a low-pass filter that can be implemented with a resistor and a capacity is enough to implement an envelope detector. This is one of the main advantages of the conventional AM modulation. It is possible to use a very simple detector, an envelope detector, to recover the modulating signal. Although the envelope detector is much simpler, it is also possible to use a coherent receiver or asynchronous receiver to demodulate a conventional amplitude modulation. Now we are going to analyze the application of this detector to a conventional amplitude modulation. This is the analytical expression for a conventional amplitude modulation. The cosine of the carrier is multiplied by the carrier amplitude times 1 plus the modulating signal with modulation index A, and a scaled version of the modulating signal. And now we are going to assume that this is the signal that we have at the input of this receiver. In this case, initially this signal is multiplied with a cosine. Here we have the receiver signal times a cosine, the conventional AM times the cosine, and using the typical identity for the product of two cosines, cosine times cosine is 1/2 cosine of the difference between the arguments. The difference between these two arguments is the difference between the phases phi c and phi, and then 1/2 times cosine of the addition of the two arguments, and the addition of the two arguments is this 2 times omega c times t plus the addition of the two phases, the carrier phase and the phase that we have here in this demodulator. This signal x of t is then filtered with a low-pass filter with the bandwidth of the modulating signal. And this filter will eliminate the terms whose spectrum is centered at 2 times the carrier frequency, the terms related with this cosine here. And finally, this means that at the output of this detector, assuming a potentially different phase phi with respect to the carrier phase, what we have is a term that is proportional to the modulating signal, this one, because MA is proportional to the modulating signal. We only have an scaling factor equal to the modulation index divided by the range of the modulating signal. And the problem is that here we have this cosine of the difference between the phases that we have in the carrier and here in this detector. It is necessary to have a coherent receiver. It is necessary to have that the phase at the receiver is equal to the carrier phase to avoid this attenuation that can be included by the cosine for different phases. And in this case, the output of the coherent receiver is just half of the carrier amplitude times 1 plus the modulating signal with modulation index A, which is proportional to the modulating signal.